Hello everyone, this is the video lecture of section 6.4, arc length. Okay, in the previous sections, in section 1.7 and 3.4, last third material, you learned about parametric equation and the curve represented by parametric equation. Okay, now let's say this is a curve represented by a parametric equation. Let's say this is x-axis, this is y-axis. So let's say this is corresponding to t equals a, t equals b. So moving like this. Let's say you have x equals f of t, y equals g of t. And let's say t runs from between 0 and b. So this is xy plane. Now in this function, let's say over here, at time tx of t, y of t. So this is your x of t. This is your y of t. Okay? So, in this motion, your x of t is kind of changing from x of 0 to x of b, from left to right, in this particular case. For y of t, which is g of t, from y of a to y of b, in this case, it's going up and down, up to this, and up again, right? So, this is a parametric curve. How do we find the length of this curve? So, length of the curve is that if you put some thread or string exactly on the curve, inelastic, not a rubber band, and then if you straighten up, you can measure the length. Now, if you don't have that tool, how are we going to find the length of this curve, right? Using this parametrization. Okay? So, this one, now think about, let's say, time interval. This is time interval from A to B. So this time t equals a will be corresponding to this point. So I'm going to call it point P0. And we're going to divide this time interval into n subintervals. Okay? This is T0, T1, T2, Tn. Let's say this is Ti minus 1, Ti. Here, as usual, delta t. We're dividing the interval, time interval from A to B, equally divide into n subintervals. So delta t is the size of the subinterval. And Ti, as usual, A plus I times delta t. Okay? So, from A, 1 delta t, 2 delta t, 3 delta t, 4 delta t, and so forth. Okay? So, when t equals t1, you will be somewhere around here, right? And somewhere around here, here. Okay? Let's say this is point P1. Let's say this is point P2, P3, P4, and so forth. Let's say this is pi minus 1, pi, and so forth, pn minus 1. Okay? So, we want to find the first approximate value of the arc length by measuring the length of each line segment connecting these 2 points. These points. Right? So, some of the lengths of these line segments will be close to the arc length if these points are close together, or if you have many subdivisions here. All right? So ti, when t equals ti, you're going to be there. So p1 equals x of t1, y of t1. Okay, let me check recording. And P2 is the point corresponding to time T2, right? And so forth. Pi minus 1. And Pi. Okay? So, we want to approximate your arc length. I'm going to call it L, arc length. Arc length, this is curve C, length of C. Will be a good approximation of the length between P0 to P1, see, P0 to P1, P0. Oh, I should have written starting from P0. T0 means A, right? And length, this length plus P1 to P2, P2 to P3, P3 to P4, and so forth. All right? So, then we want to find good approximate value for that. Okay? So, let's take a look at, in a typical case, not this, let's say this is pi, I minus pi. Okay? Let's say your typical case, pi minus 1 to pi, and then this line segment. Okay? We want to find the line segment length. Now, let's draw a right triangle out of this. Now, what is it? This is x of ti, y of ti. This is x of ti minus 1, y of ti minus 1. Right? Then, this length is, we call it delta xi. Delta means changing something, so change in x coordinate. Well, specifically that means x of ti minus x of ti minus 1. Right? This is what I call delta yi, changing y coordinate. Delta yi, which is y of ti minus y of ti minus 1. Okay? Now our x of t means f of t, y of t means g of t. These are all assumed to be differentiable functions. Okay? All differentiable functions on this and continuous on this full closed interval. Now, then delta, look at this, delta y xi over delta t, this delta t, time difference between this point to this point, right? We're moving in that direction right now. That one, which is x of ti minus x of ti minus 1, delta t is ti minus ti minus 1, right? So this one, this is average rate of change, will be exactly same as the derivative somewhere ti star for some ti star, right? In this interval. Because mean value theorem. Mean value theorem. Because your function x of t or f of t is continuous on this interval and differential inside because of this condition, then you must have that point where instantaneous rate of change will be same as average rate of change. Therefore, your delta xi, but then the problem is actually different from y. So let's do this one. Exactly same, but at least we can say that this is really, really close to at least x prime of ti. At least it will be very close to this. Okay? If you want, you can put midpoint, right? That would be even better approximation. That's why delta xi will be very, very close to bar delta t, if delta t is small, which means if n is small, right? Now, likewise, delta yi over delta t, y of t I minus 1 over ti minus, so this is delta t again, really close to the derivative in the middle, right? So, likewise, delta yi is really close to this derivative, y prime of ti bar. Ti bar is the midpoint, ti minus 1 in the middle, okay? So, your length pi minus 2pi is square root of delta xi squared, delta yi squared, square root by Pythagorean theorem, which is in turn very, very good approximation. Approximate value is this delta prime ti squared, delta t squared, and y prime of ti bar squared, delta t squared bar. Now you factor out x prime ti bar squared, y prime ti bar squared, so this delta t square square root. So that would be, that is exact, x prime ti bar square, y prime ti bar entire square, square root, and square root of delta t square is just delta t. Okay? So, this is a very good approximation. Therefore, your total arc length will be approximated by summation of pi minus 2pi here, alright, which is square root of x prime of ti bar squared y prime ti bar square root delta t. Now this approximation and this function, both of them are getting better and better as n goes to infinity, as n is larger and larger, smaller and smaller subdivision is closer and closer each point. So this, piecewise line signal approximation to the curve will be getting better and better, that approximation. So if you imagine the limit as n goes to infinity, that value will definitely be approaching the true value of the arc length. So we can conclude that as a limit as n goes to infinity of this one, derivative x prime squared what is it? Summation limit as n goes to infinity. Limit of Riemann sum is what we call definite integral of this function. Y prime of t squared plus x prime of t squared plus y prime of t squared dt. Okay? All right. Okay, so this is the formula. When you have a parametric equation, the arc length of the curve will be given by definite integral of this function, square root of x component function's derivative squared plus y component function's derivative squared from a to b. Okay? All right. Now let's do some examples then. You memorize the formula of the circumference of a circle as 2 pi r if your circle's radius is r, right? Have you ever seen a proof? You're just told and you just believed it. And yeah, you're correct. That is correct information, so you can believe it. But you have never proven it. So this might be the first time you see the proof, one version of the proof. Okay? So let's find the circumference of a circle with radius r. In the section 1.7, we learned that that circle can be parametrized like this. And the t being 0 to 2 pi. Right? Then it'll go through from here, 1, 0, counterclockwise. Come back to this one turn. That's what we learned. So let's find the arc length from here to here. One turn, so circumference. The arc length L is from 0 to, okay, first of all, what is x prime of t? Minus r sine of t, y prime of t, cosine of t. So we need this, right? We need this. Square root of x x prime of t squared plus y prime of t squared is r squared sine squared t, r squared cosine squared t, r squared sine squared t cosine squared t. Okay? And that is 1. So, square root of r squared, obviously our r is positive. It is just r. Right? So, your arc length, by definition, by this formula, from 0 to 2 pi, x prime of t squared, y prime of t squared, dt is nothing but 0 to 2 pi, constant function r dt, right? So, that is rt from 0 to 2 pi, r times 2 pi minus 0, 2 pi r, as we expected. Okay? Alright. So we proved this one. Now, because of this, we can do interesting things, like what if arc length you want to know, the curve whose arc length you want to know about, is given by y equals f of x, the x between a and b, like this, a to b. What can we do about this? Well, in section 1.7, we can have a natural parametrization as x equals t, y equals f of t, right? And t is going from a to b, right? So we can use this parametrization for the arc length. So what is x prime of t squared, y prime of t squared? X prime of t is 1. 1 squared is 1. This is f prime of t squared. Therefore, according to the arc length formula, this is from a to b square root of 1 plus f prime of t squared dt. Now, x was equal to t. T is not an important choice because this is the variable, dummy variable, the temporary variable you are using only in this calculation of definite integral. So we can choose any other variable, like original variable x. The value will be exactly the same, right? That's why you have this formula. So, when you're given by parametry equation, this is your formula. Or, if you're given by graph of a function, then you can do 1 plus f prime of x squared dx. Okay? So, let's do other example. Second example. That is example 2. Find the length of the arc of the curve y equals 1/2 of x squared from 0, 0 to 1, 1/2. Part of the parabola, 1, 1/2, 0, 0, part of the graph. Okay, y equals 1/2 x squared. Well, so your arc length will be from 0 to 1, 0 to 1, square root of 1 plus f prime of x, which is x, right? F prime is 1/2 times 2x, x. That one square dx. Okay? Now we can use some trick, substitution for this. This is more complicated than you think, but that is possible. That's why you have a result. You have a antiderivatives in this, integral table at the, I think, a back page of your textbook. Okay, so that is number 21 actually. When you look at carbon paper, page 6 on the back of your textbook, number 21, integral formula number 21, give you this. That is, it's definitely into this x over 2 square root of 1 plus x squared plus 1/2 ln of x plus square root of 1 plus x squared. So you have to do from 0 to 1, 0 to 1. Okay? So when you're plugging in 1, square root of 2 over 2, if you're plugging in 0 is 0. Alright? Plus 1/2. Plugging in 1. ln of 1 plus square root of 2 minus plugging in 0 ln of 1, which is 0. You have square root of 2 over 2 plus ln of 1 plus square root of 2 over 2. That's the exact value of the arc length. Okay? Now, one last thing is that, what if your graph is now y equals f of x, but x equals g of y, x as a function of y, from c to d. Then you're going to use y equals t, this is g of t, right? T from c to d. Then this will be g prime of t squared and 1 squared, which is 1. So it's going to be 1 plus g prime of t squared dt from c to d, or c to d 1 plus g prime of y squared dy. Okay? Exactly same form, because it's just the exchange of the rows of x and y. Okay? So, let's do example 7, which is same as number 9 on page 459. 459, number 9. That is one of the homework problems. Okay? This is homework problem. So I'm going to give you how to start. C to d, c equals 0, d equals 1, g of y. This is your g of y. Okay? So your g prime of y equals 3 over 2, y to the 1/2, right? So your arc length will be integral from 0 to 1, square root of 1 plus square of this, right? 9 over 4, y. Okay, I'm going to just write it. Inverse it, why not? dy. 0 to 1, 1 plus, so 9 over 4 times y. This is it. You just have to calculate this definite integral. That's easy integral. If you have 9 over 4y, du equals 9 over 4 dy. So you can change it to integration with respect to y. Okay? Alright. So this was a rather short section. Alright? So we learned how to get arc length of a curve first when the curve is represented by a Taylor-Tripp equation. Okay? And this is the result. When you have x equals f of t, y equals g of t, f prime of t squared, g prime of t squared square root, and definite integral. And using that one, we derive the formula of arc length when the curve is given by y equals f of x as a graph of a function f of x from a to b. It's equal to 1 plus f prime of x squared, integral from a to b. Likewise, if it is given as x of g of y from c to d, the integral from c to d is square root of 1 plus g prime of y squared. Okay? Alright, that's the end of section 6.4. Thank you. See you next time.